everything will be okay. So good to see everyone, and hello everyone, and thanks for attending OCP this week. For those of you who don't know me, my name is Shahar Noy, and I run the storage solution organization within Marvell. Many people ask me, hey, at the high level, what are you guys doing? And if I need to summarize it, we are responsible for providing solutions to improve utilization of storage at a high level. Now, today we will focus on how we can improve HDD utilization at the data center using hardware components to convert HDD into NVMe and to virtualize. Sorry. So we will start with definition of what is storage virtualization and mainly how it's being managed today for SSDs. We will explore the shift from software-based solution into hardware-based solution using SRLV, which is a PCIe definition of how to share PCIe resources across virtual machines. In the second part, we will review, and I want to say in some way we will repeat some of the benefits of NVMe HDD, but we will also tie this together with the first section, right? NVMe HDDs use PCIe. If you have storage virtualization capable accelerator like SRLV based solution, combine it with NVMe HDD gives you even more benefits. We will show how everything connects, and then we walk you through a demo. And the demo will show you the functionality aspect of the solution, but also there will be, I want to say, a very interesting discussion around the performance results of this demo. Now, let's start, right? So hypervisors, if you guys are almost as old as I am, and you guys have been around for a while, you know that, I think I want to say the VMware, the first server, I think it was the GSX release. And hypervisor 2 decades ago had, a novel concept of, hey, how we can spin more VMs out of a single hardware resource, right? As those resources continue and grow, mainly the CPU and the capabilities of the CPU, multi-cores, multi-threads, the hypervisors evolve with them and were able to spin more and more VMs, right? They grow, the hypervisor grew together, I want to say, with the advancements in x86 and the advancements in ARM processor. However, hypervisors are always challenged when you look into IOs, because historically a hypervisor will have at its back, which can be a NIC, the unit that's responsible for sending IOs over the network, or it can be some sort of a storage controller. Like in our case, it can be HBA, it can be a PCIe switch, right, that manage all the IO to the storage. Now, the way hypervisor is structured is that it would need to emulate any piece of this IO up to the VMs. It will need to emulate the networking function, it will need to emulate some storage function, and as we add more and more IOs, right, at the back end, hypervisors are being challenged and they're becoming the bottlenecks of the system. So how do we resolve it, right? How do we reduce the emulation and the software overload from the hypervisor? Ta-da, enter SRLV. Now, what is SRLV? SRLV, once again, provides, it's a PCI SIG definition, right? And it provides additional definitional capabilities to the PCI Express specification to enable multiple VMs to share PCIe hardware resources, right? So it's key here that the fundamental change is that if I can have certain hardware capabilities to offload this, I can also start connecting the VMs directly with this SRLV capable device, in this case, SRLV storage controller device. Now, what's the benefits, the main benefit in doing this? First and foremost, the VM can connect directly, can DMA into this SRLV capable bridge. By doing this, you reduce some of the overhead, so you get almost bare metal performance. You get almost the raw performance of the device that sits behind the storage controller. The second biggest benefit is that by the fact that you bypass the hypervisor, you don't use the x86 or the ARM server cycles here, and those cycles are becoming more available to the VM, which mean, or to the containers nowadays, right? So I can run more applications, I can support more users on my existing x86, which is a huge, huge benefit for all the cloud providers. Now, to achieve this, to achieve SRLV architecture, the spec distinguish between two types of functions. We have the physical function, the PF, and the physical function is a full feature PCIe function. You can discover this, you can manage it, you can manipulate. It technically looks like any other PCIe device which is attached to the host. You also have a full configuration space. Now, the virtual function is a lightweight version of this architecture. So only certain functions can be supported, and those are mainly in terms of like how we move the data in and out. So let's take an example. Let's explore the storage controller. If I have a single port storage controller, I will expose it up as a physical function to the host. And then every time I'm carving another portion of the storage that sits underneath, I will assign it through a VF to the designated VM. And I will show you more examples. If I have a dual port, let's say a storage controller, then each will get its own physical function. So again, a very, very cool technology. There's a lot of smart people here on the call that I believe knows more about SRLV than myself. But what we see in the market that if in the last decade, SRLV was very popular with networking cards, right? Because there is almost any networking card, the basic NICs, the most advanced smart NICs, they all support SRLV for networking. But only recently we start having more and more discussions about storage devices which are SRLV capable. And we'll show you in the demo today how we support it. But in essence, they provide the same benefits like a networking card. But in terms of providing this to network resources, now we provide it to SSD and potentially HDD resources going forward. Now, let's visit the second topic, which is NVMe HDD. So as you know, HDD are predominantly use SAS and SATA interfaces today, and those interfaces speaks the SCSI or the AHCI language, right? Those are the protocols that runs on top of those physical interfaces. When we look into what's happening now, and I believe Muhammad covered a lot of this in his previous section, there is a proliferation of PCIe because all the interconnect today in the server, if you think about it, is PCIe. GPUs are connected through PCIe. The networking cards are connected through PCIe. The proliferation of NVMe SSD devices, storage class memory devices, all of those force the SoC vendors like the x86, the AMDs, and the Intels of the world to provide more PCIe lanes embedded inside their SoCs. So if we can also create HDD PCIe device, we can now have shelves with multi-tier storage. You can put storage class memory, SSDs, TLCs, MLCs, QLC, and HDD in a single shelf, which provide a lot of benefit for the data center designer, right, or the data center owner in terms of how they want to structure their different tiered storage. The other benefit in this case, and this is, I think, also fresh from the FMS show, if you look into most of the storage accelerators today, if we look into key value acceleration, if you look into compression, encryption, all of the new accelerators are being designed for PCIe, predominantly to support SSDs. If we design PCIe HDDs and NVMe HDDs, they can benefit from this, right? They can work with the same highly advanced NVMe accelerators that exist out there in the market. The second main benefit is consolidating the protocols, right? Having a single protocol to talk to SSD, storage class memory, and HDD. And the main benefit here is that we see how certain operating systems, certain applications, certain databases, right, are kind of like tuning more and more into NVMe. If we can take all of those, right, if we can take this this whole application layer and just know that we're speaking one language down, we're simplifying the architecture. We're removing the need to support specific SCSI and AHCI drivers as we see today in certain HBA solutions. So again, it's all about simplifying the data center, making it more, not only simple to consume, but also simple to deploy. The other interesting aspect of NVMe is the proliferation of NVMe OF. So NVMe OF gains momentum. We know about the SmartNICs that support NVMe OF. We know about the SmartNICs falls under the FBOF architecture, the JBOF architecture. A lot of discussions about EBOF, right? Ethernet bunch of flash that comes to the market. So NVMe OF becomes more and more available. Now, what is NVMe OF? Is a layer above NVMe. If you have HDDs that speaks NVMe, they can also be a good fit for an NVMe OF architecture. And today, most of the new NVMe OF deployment for scale out or for disaggregation are actually taking advantage over NVMe OF. So again, we can take HDDs now together with all other type of medias that we have, put them in a scale out solution and give the architects, give the data center designers kind of like peace of mind in terms of how they can mix and match the tiered storage with a single interface, with a single protocol. Now, the third element, which I want to tie it back to the first slide, is that if I have NVMe PCIe HDD, it's not just about reaping all the benefits of everything which is out there right now, but also going forward, being able to put those NVMe HDDs behind SRLV capable controllers, which make HDD now able to support hardware virtualization, which is much more efficient way to use your resources in a data center. Mainly in a data center, they use highly virtualized workloads. Now let's look how everything, if you put it all together, right, comparing to the first slide, how it would look like. We have the same VMs cutting through the SRLV storage controller, bypassing the hypervisor or using a light version of the hypervisor. They can already connect with NVMe SSDs, and now they can seamlessly connect with NVMe HDD. Very simple. So for someone who builds his own platform as a service or infrastructure as a service, and they need this granularity of how you carve more capacity or more performance per user, this architecture is very, very attractive to use going forward. Now, let's go into the demo. And before I play the demo, I want to show you all the building blocks and explain a little bit about the building blocks, about how we configure them and how they can be configured. So you guys can process more how, the benefits or how you can use it in your own environment. You can see here that I will start from the bottom. We partnered with Toshiba. I apologize to the WD and the Seagate people on the call. Next time we'll do a better job talking to you in advance about those demos. But we partnered with Toshiba for this demo using their nearline MG8 SATA HDD. We have 4 of those HDDs, and each and one is a physical device, right, from 0 to 3. Each SATA component, or 2 of the SATA component, 2 of the SATA drives, will get connected through Marvell 1388. The 1388 is a fairly simple a SATA to PCIe bridge, right? We connect 2 of those drives and expose them up to the system as over a single PCIe bus. And then we have the 2241, which is our more sophisticated solution. So the 2241 is what we announced a while back as NVMe switch. For many people, it looks like a PCIe switch, but the reason we call this NVMe switch is because we have more capabilities. Now, in this demo, the intelligence that the 2241 adds into this demo is that first, it will enable SRLV. Second, it will manage all the I/O traffic. And this is the magic. There is a lot that needs to be done here in terms of like how you throttle the I/Os down from the host to the different devices. The 2241 will also do the namespace to virtual function mapping, and will do the protocol conversion. So as we move from NVMe, right, to HCI, there's some protocol conversion that needs to happen. So all of this goodness, all of this intelligence resides here. And an interesting element, or I want to say key benefit of the 2241 is that it can add a layer of virtualization by carving as many namespaces as required across the drives that sits underneath. So let me try and explain it. Let's say we have a user who wants to buy a lot of capacity. Let's say in this case, 4 drives, each 16 terabyte, total 64 terabyte, and want to expose them up as a single namespace. The 2241 will be able to unify, right, across all of those, all of this capacity, all of those addresses, and expose it as a single namespace. But maybe you have a customer who wants to put 128 tenants and create 128 namespaces across those drives. The 2241 can be configured or enable you to configure it in a way that we can add more namespaces per device. Again, it's all virtualized. So in this demo, to keep it simple, what we did, we assigned a single namespace. The 2241 will create a single namespace per HDD, so a total of 4 namespaces. Each namespace is assigned to a VF, and every VF is assigned to a virtual machine. So for example, when virtual machine 0 comes up, it will connect directly to virtual function 0 that will see namespace 0 that resides in HDD 0. Okay, very simple, trying to keep the demo very, very simple, but there's ways to, again, change the virtualization scheme with those devices. From a hardware perspective, can you guys still see my screen? I see a little bit white. Can you guys still see my screen? I apologize.
Yes, we can still see it.
Okay, perfect. So we took a super micro quad socket device. We only populated it with a single processor, the Gold 6148 here. The hypervisor is actually KVM, right? Open source Linux solution that runs Ubuntu 18.04 on LTS server. All the VMs that we're spinning here are Linux, and this is the version of the Linux. And again, going back, the 2241 will act as the storage IOV accelerator. The 1388 is the SATA to PCIe controller, and the Toshiba HDD that I mentioned. Let me take you now through the demo, and we'll go to Lance.
Welcome to the Marvell Virtualization NVMe HDD demo. The purpose of this demo is to demonstrate the capability of NVMe virtualization over SATA HDDs. We have 2241 connected to the host, and we have 13AA connected to SATA HDDs, which forms the Marvell latest NVMe to HCI adapter that provides the NVMe interface to SATA HDDs. Let's run the demo now. Base OS. Five PCIe functions are reported. They are function 0 to function 4 on bus 99. Function 0 is physical function, and function 1 to function 4 are virtual function. There are 4 namespaces reported, and each of them is associated with one of the virtual function NVMe controller. They are built up from the 4 backend attached SATA HDDs. Now we are launching the 4 VMs. First, combine the VF1 from base OS and pass through VF1 controller with its associated namespace to the VM. Then launching the VM1 with VF1 attached. Now we can see VM1 is launched. With one pass-through PCIe function. one NVMe namespace attached to this PCIe function NVMe controller. Repeat the steps for the other 3 here and launching the 3 remaining VMs. Now we have 4 VMs. Let's launch FIO on VM to exercise NVMe I/O targeting on SATA HDDs and see cluster performance. The workload is 128K sequential read with 1 job and 32 queue depth. We can see the bandwidth for each virtualized namespace is around 256 megabytes per second.
So I apologize. You can see here the four VMs technically, and we highlight the FIO sequential speed per unit. But let me share the table. We have another table to share the results with you, and the results are quite interesting. So what we did here, we looked into the traditional random performance, 4 kilobytes, traditional sequential test was 128 kilobyte, and we compared direct attached HDD, the same HDD, through the SATA bridge, so through the same 1388. 1388 can also act as a port multiplier. And then we compared it to the demo, the architecture that I showed in the previous slide, where we also have this IOV capability introduced into the mix. So this will speak SATA all the way down. This will speak, sorry, AHCI all the way down. This will speak NVMe all the way down through the IOV bridge. What's interesting is that in the random performance, we actually got better numbers, right? Like in this case, 1.07 more or 1.15 more than the SATA direct attach. And we believe this is attributed to 2 factors. One is the fact that we speak NVMe down, and we also make a very basic translation of NVMe to AHCI. We reduce some of the overhead. The second one is the fact that the 2241 is so fast and is the first unit to service all the four drives underneath, eliminate some of the bottlenecks. And this is why you see that in a random, in a highly fragmented use cases, we actually get a little bit more performance. Then if you look into the sequential, the more traditional sequential test, we actually get a hit of up to 1.3, 1.4% performance degradation. When we talk with our customers about using this type of solution, they say that relatively to the benefit of being able now to carve a sequential speed of HDD across a couple of tenants. Let's say a couple of tenants require different video streams. So the reduction in performance by 1.5% is almost negligible compared to the benefit of being able to carve this HDD across a couple of tenants. So pretty interesting test results here. And we, again, would love to collaborate with the industry and figure this a little bit more down the road. After we did the VM test, we also thought about another use case that we didn't talk about at the beginning of this call, but what about bare metal, right? There's also a big deployment of bare metal servers out there. And what if the user will bring his own hypervisor? We don't have control on this hypervisor, but we still want to give the customer the benefit of using those HDDs in different capacities, or again, I would say either carving more namespaces out of those drives or splitting the capacity across tenants. You can see here that we can still expose those drives as namespaces. In this case, it's a 1-to-1 ratio, but the 2241 can help you with configuring it slightly differently, and also get those namespaces exposed to the users. So we ran the same benchmarking, but now without the virtual functions, right? Without the actual guest, and we got very similar results. So this is bare metal performance results that where we run FIO per namespace. And you can see here still on the random side of things, we get improvement. We believe, again, thanks to the fact that we use the NVMe protocol and thanks to the 2241 ability to manage more fragmented, or I want to say random throughput compared to just the SATA port multiplier itself. And we see a similar 1.5% overhead when we go into sequential speeds. So as Mohammed said I think it is a previous presentation, please join us in the NVMe working group and help to drive the future of HDD interfaces. Even at Marvell, we believe that HDDs still provide lion's share of bit capacity at the data center, and our mission is to make them more efficient so we can improve on HDD utilization across the various use cases. Thanks for listening today, and I would be more than happy to take any questions.
Thanks, Shahar. And as far as questions, I think we need to avert those to the actual FN virtual platform since we're out of time on this track. But please direct all questions for Shahar and team onto that track.
Okay, thank you so much, guys.
Thanks, Shahar. If you can stop sharing your screen, then I think, what do you call it? Jason can take control because I think he's up next.
And then up next.
Yeah, let me do this. For some reason, I think that the problem I had is that my Zoom bar keeps freezing whenever I try to do something there. So give me a second.
Mm-hmm.
And I might need to drop off and come back to this session.
There we go. I think I'm able to project if everyone's able to see mine.
Actually, what I'm showing is both of you sharing your screen, which is interesting. I can, let's see. Okay, I think I can force share, stop share from Shahar, but it's not letting me. Go ahead and try to share yours.
Mine should be sharing.
Interesting.